right, guys, let's go ahead and get started. We're going to pick up where we left off last week. We were starting to talk about urine formation, and really we just kind of outlined the four basic steps that are required to generate urine through the filtration of plasma. And those four steps are listed at the top there: glomerular filtration, tubular reabsorption, tubular secretion, and water concentration. So we're going to take these one at a time. We'll probably get through maybe a couple of them today, and then the rest will be for when we get back from our Thanksgiving break. So we covered those terms: urine, tubular fluid versus glomerular filtrate. Today we're going to be focusing largely on how the glomerular filtrate is produced. Okay. So, glomerular filtration is the process by which we send blood into this structure called the glomerular capsule. So we have this blood vessel that is encapsulated. Not very many places in the body can we point to where a blood vessel is surrounded by and encapsulated by some other structure, right? Usually blood vessels are simply taking blood from point A to point B. But here in the kidney, we have this twisting and folding of a blood vessel that is surrounded by a structure. And this structure, the glomerular capsule, is just here to catch whatever leaves the blood vessel. So we're basically pushing, we're screening things out of the bloodstream here within the glomerular capillaries, and whatever comes out of the glomerular capillaries is captured by the glomerular capsule, and then potentially will be treated as waste as it moves on down the proximal convoluted tubule. So we spent just a little bit of time talking about what might come out, and we'll provide some more specificity to that today. But certainly one of the things that is removed from the blood vessel is a pretty significant amount of water. So water is moved out of the blood vessel. And then as a catch-all, we can say that any number of solutes. So these are going to be our things like calcium ions, sodium, glucose, the waste, the nitrogenous waste, urea, right? So any number of things that were dissolved in the water are also going to be filtered out. So the capsular space can be thought of as anywhere between here and there. So all of these items that are being filtered out of the blood are now contained within the capsular space, and whatever is in that capsular space, going back a slide, that is what we refer to as the glomerular filtrate. Whatever previously existed in the blood vessel and is now within this space called the capsular space. This is as it says here, a special case of capillary filtration. So let's just look at how ordinarily things ought to work. So a capillary is any place in the body where you have an artery branching to smaller and smaller blood vessels. And then eventually those capillaries give way to the venous system, aka the veins. And on the other side, we have just that. So this is a normal capillary. And at the location, the same thing is occurring. Things like water are escaping and things like solutes are escaping. But the difference is that there are cells that might be taking up those things that escape from a blood vessel. But over here, there isn't a cell that's absorbing those materials that might be leaving the bloodstream. We're capturing it all inside of this glomerular capsule. And notice also different in this capillary is and remains an artery. Whereas in a normal capillary, at the capillary, the blood vessel gives way to veins. So what drives the movement of the solutes out? It's pressure. If I have a significant amount of pressure and I have essentially a large enough hole in my blood vessel, then things can escape out. So what happens at a capillary is that pressure increases and my blood vessel becomes more permeable. The reason things weren't escaping back here is because my pressure was lower because it was a bigger diameter, and also my blood vessel wasn't very permeable. I didn't have very large gaps between the cells. So at a capillary, I have an increase in pressure, blood pressure. I have a blood vessel that's more permeable, which means having larger spaces for things to escape, and then, if that's the case, things will be pushed out. So that tells us that over here, similarly, in order for this to work, I have to have some amount of pressure inside this blood vessel, and I have to have some amount of permeability, right? I have to have some size of hole to allow things to escape. So that's what we're going to explore next, the permeability and the pressure that is inside this blood vessel. Questions there? All right, the first thing that we're going to look at is what we call the filtration membrane. What we're going to do here is imagine that we can zoom in on the surface of that blood vessel and kind of inspect its structure and describe what it is that's there. So go back over to that side, let's sketch it out. Okay, first off, we have to recognize that blood vessels, veins and arteries, they're just made out of cells. So we can think of a blood vessel wall as being cells that are connected to each other. And so long as they are connected to each other, there's very little permeability, right? To get out of that blood vessel, something has to essentially go through a cell. Once this blood vessel goes into the glomerular capsule, so here, what starts happening is we start putting some space between the cells that make up the blood vessel wall. Put little gaps between the cells. And so those little gaps, those are the pores, and now it's very easy for things to escape out of the blood vessel, or at least easier. This is what we refer to as the fenestrated endothelium. So the fenestrated endothelium is the gaps that start to appear between cells within the blood vessel. So before capillary, I don't have those gaps. At a capillary, I need those gaps in order for things to easily escape from the blood vessel. You do not have to remember the nanometer filtration pore size. We'll say a couple of things about the specific size later, but don't worry about the specific number value right now.
So that happens with any capillary?
That happens with any capillary.
Okay.
This next part also happens with any capillary. Outside of the blood vessel, are really to the side of the to the outside surface of this cell, you also have basement membrane. Basement membrane is a collection of protein fibers. So to the outside of these blood vessels, you've got what is called basement membrane. And so it's like this mesh of protein. And so if something is going to escape from the bloodstream, it has to pass between the cells, and then it also has to pass through this mesh of proteins. So that's a part of the filtration process. So the basement membrane, you don't have to remember the specific characteristics, so long as we know that it is a collection of proteins, that is sufficient. And then the other quality that'll come back of some importance later is knowing that that blue basement membrane maintains a negative charge. Okay, it maintains a negative charge. We'll tie that into albumin, as you can already see there. We'll talk about it in just a moment. So now we have essentially two things that we have to pass through so far to escape the blood vessel. We have to squeeze between two cells That's the fenestrated endothelium. And then we have to move through those protein fibers, that mesh of protein fibers. And then still, to the outside of that, we have something called filtration slits. The cells of this capillary, this blood vessel, this capillary, is covered with another cell type. There are these cells called podocytes that are actually covering the surface of this blood vessel. So if you could imagine kind of cracking this thing open, you wouldn't see the blood vessel. You would actually see these other cells called podocytes that cover the blood vessel. And they're kind of creepy looking cells. I'm going to exaggerate, but they kind of create these little arms. Let's say this is the podocyte. I'll abbreviate. So this is the podocyte. And they create these little structures, sometimes referred to as paravascular feet. I don't know if I have it on here. I've got pedestals on here. That's another term for them. But as long as you know, they create these little structures that attach to the cell surface. And so now you can see that if I want to move out here, if I want to get out of this blood vessel, I have to squeeze between all of that. I have to go through the blood vessel wall, I have to go through the basement membrane, and then I have to go between these little structures called pedestals that are wrapped around the blood vessel. The analogy the only one that ever comes to mind for describing these podocytes is as if you had a garden hose or any hose that had a leak in it, right? And suddenly you needed to stop maybe this garden hose has a rupture and it's just spraying you in the face, right? So you didn't think to like pinch it off, but instead you just wrapped your hands around it, right? Water's still gonna kind of start squirting out between your fingers, right? But it's still gonna come out, but you're slowing the process. That's kind of what these are. They're like you got a leaky hose, so it's already somewhat permeable, and these structures are kind of like somebody wrapping their fingers around it, and from this side you'll have others coming in this direction, and so you end up closing it off, but not completely, because things can still squeeze between. So collectively now, those three layers, the podocyte cells, the basement membrane, and the fenestrated endothelium, collectively that is what we refer to as the filtration membrane. To escape the blood and get into the filtration space here, the capsular space, you've got to get through those three layers. All right, let's come back and mention this negative charge that's now mentioned in a couple of locations here. Many of the proteins, nearly all, I can't think of an exception, there probably is. Many of the protein molecules that we actually want to keep, they come in and they come out. We don't want to filter them out. They are negatively charged. So we have this mechanical barrier, right, to filtration, this material that you have to pass through. But then we also have this repulsive barrier that the basement membrane and portions of the podocytes, they maintain a negative charge. So when these negatively charged molecules try to escape, they're repelled back, like two ends of a magnet that both have a negative charge, they're repelled back. So even though it is mentioned in context with the other layers, we kind of need to think about it in terms of this additional method that we use to repel and keep certain materials back inside the blood vessel. So we have three mechanical layers, and then this repulsive barrier because of the negative charge that's present in the basement membrane. And anions in anion. We haven't talked about anions for quite some time. Chapter 3 stuff, that's just a negatively charged something. And an anion is just a negatively charged something that we keep back. So, for this example, just literally think about a hole in a water hose. You've got your hands wrapped around it, and all the things that water has to pass through to finally get to the outside. That's kind of what we have going on here. Questions on simply what the filtration membrane is made of.
So what exactly is albumin?
Oh, this is albumin. I don't know where I put it. Somewhere. Oh, there it is. This is our most abundant plasma protein. Albumin. So out of all the proteins that exist within the bloodstream, albumin is the most abundant. Other questions? Okay, so now this is similar to the drawing I was making over there. They've got it turned this way, right? So this is the blood vessel, the blue is the basement membrane, and they use this pretty brown color for their podocytes, but same idea here. And this is giving you an indication of what can make it through and the kinds of things that are held back. Now, not now, but eventually I'll give you a specific list of things that I want you to know indefinitely. Here are some things that make it through, and here are some things that are held back. But for now, we're just going to talk about the structure. So that picture is representing what I tried to sketch over there, albeit on a vertical plane instead of a horizontal plane. Here's an actual electron scanning image of them, right? So that little blue guy is a podocyte, and you can see how these little structures just wrap around the blood vessel. Okay, so now here's that slide. Sorry, I guess it was coming up sooner than I thought. Here's the slide on the items that you'll need to know in terms of can it pass through or not. So up at the top, it basically says any molecule smaller than 3 nanometers. If you're smaller than 3 nanometers, typically that means you're escaping the bloodstream here at this point. So here's the short list of examples of those molecules. Right? It's not all inclusive, there are many others. So that means water, electrolytes, and for electrolytes, just think sodium, potassium, calcium, glucose molecule, fatty acids, amino acids, all of those nitrogenous wastes that we mentioned on our first day of urinary system discussion, and vitamins. So all of those things, all of those being solutes, they find their way out of the bloodstream. Now you can look at that list and you can see that, hey, a lot of those things I don't want to expel as urinary waste. So we'll talk later about how many of these solutes are returned right back to the bloodstream. So this filtration system early on is overly effective, right? We filter out lots of things only to almost immediately put them back into the bloodstream. Things that cannot, or ordinarily under normal conditions, should not be filtered out of the blood. So we can say, well, things that are significantly larger than 3 nanometers, right? In other words, things that have, oh, wait a minute, sorry. Skip this. This is the part I was going to skip. Don't worry about this bottom board. We will say something about that, but it's a better slide for today. So right now, we just got our list of items that we have. So now, let's, well, I guess that's just not here. Thought I had a list for things that stay back. We'll create a very small list, okay? So for the things that do not get filtered out, Plasma proteins. Plasma proteins should not get filtered out of the bloodstream. Most of these actually mentioned the other day. The cells. That's a catch-all for any number of cells. Red blood cells, neutrophils, lymphocytes, white blood cells in general, in other words. Proteins and cells should not get filtered out. And then, so we've got proteins, we've got cells, and minimally we just need to know if that means red blood cells and white blood cells. And then the third one is technically already defined by what I said first, the proteins, but this is the specific case. The third one is protein-bound solutes. Protein-bound solutes. And even though we're largely skipping that bottom bullet, I'll give you one example from that bottom bullet. So let's take something like calcium. Well, calcium is an electrolyte. So based on that definition and the fact that it is well under 3 nanometers, that tells us that calcium should find its way here. But I don't always want to lose calcium. Sometimes I don't want to take the risk of losing calcium, even though I can put calcium back in later. So a lot of times what you will do is we'll take certain molecules or certain electrolytes and we will bind them to a protein. And we've actually already talked about this, right? We talked about carbon dioxide getting bound to proteins. Partially the reason that we do that, we bind that CO2 to proteins, is so that it doesn't escape here at the kidney. So we bind certain solutes to proteins because the proteins don't get filtered out. And if the proteins don't get filtered out, then we can attach something to a protein, and then that thing, whatever it happens to be, also doesn't get filtered out. So just to run through that again, things that shouldn't get filtered out, proteins of any type, white and red blood cells, and then protein-bound solutes, solutes that we attach to proteins to keep them from being filtered out. Questions on what can and typically does not make its way through the filtration process? There. All right. Let's talk about the pressure. So we said that even under normal capillaries earlier, we said that what drives the material out of your blood vessel at a capillary is the pressure. There has to be a sufficient amount of blood pressure, hydrostatic blood pressure, in order to force the molecules out, right? Nothing's coming out of a garden hose unless there's enough pressure inside that garden hose to force the water out. So there are multiple pressures here that we have to take into consideration when it comes to how this filtration system works. So our first pressure that we're going to identify is called the blood hydrostatic pressure. This is just simply blood pressure, right? And really we're just reminding ourselves here that blood is a hydrostatic pressure. And a hydrostatic pressure is just the force of a fluid pushed against the walls of its container, right? So water in a garden hose has hydrostatic pressure, and blood in an artery therefore also has hydrostatic pressure, and we simply call that hydrostatic pressure blood pressure. So here we're saying that the pressure inside that blood vessel is 60. It is 60 millimeters mercury. That's the pressure inside one of those blood vessels. Now, earlier we drew a typical blood vessel, right? Or a typical capillary. We said that it uses branches, and then it goes to the venous system. The pressure inside that blood vessel is typically around 10 millimeters of mercury. So 60 inside that tube but 10 inside a blood vessel capillary just about anywhere else in your body. So we got two questions to answer, how and why. How's easy, why is it a little bit more complicated? First thing we're going to answer is, how is it that the pressure is so much higher here than in a normal blood vessel, okay, than in a normal capillary elsewhere? And it basically tells you here is because the afferent is much bigger than the efferent. Whereas in a normal capillary, whatever the diameter of my blood vessel flowing to, typically sometimes even smaller than, but at least equal to the diameter of my blood vessels on this side. So we maintain the diameter. But here, we don't do that. We narrow the blood vessel as we get to this point. And this would be the equivalent of having a garden hose, right, and just squeezing on it, right? If I squeeze here, so to speak, I narrow that blood vessel, well then pressure has to build up back this direction. So the how we get to having a higher blood pressure inside this capillary is simply by having two diameters, a larger inflow diameter and a smaller outflow diameter. That's going to cause an increase in pressure. Okay, so then we need to answer the why. Why do we have a much higher, as much as 6 times higher blood pressure inside that blood vessel as compared to blood vessels and capillaries elsewhere in the body? And the reason is because this blood vessel is fighting against other pressures that blood vessel is not. When this blood vessel loses H2O, that H2O goes in one of two places. It either is absorbed by the tissues that surround this blood vessel, or it is simply reabsorbed by the downstream blood vessel. It's reabsorbed by the veins. But if I encapsulated this, right, if I put a bubble around all of this, that H2O can't go anywhere. It accumulates in this capsule. And so what would happen to the pressure inside that space? It would go up as the fluid leaves. And that is exactly what happens here. So because I am losing water to the outside, which I am anywhere in any capillary, but have encapsulated this structure, I start having rising pressure in the capsular space. And so I have to fight against that rising pressure. Ordinary capillary pressure wouldn't be enough to overcome it. So I have to have a higher than normal blood pressure to overcome the rising capillary pressure. So we're actually going to define that value. We call this the hydrostatic capsular pressure, hydrostatic pressure in the capsular space. In other words, we can say, hey, there's fluid inside that tube. What's its pressure? And now that we have encapsulated this structure, we can also say that same thing here. There's fluid in this structure. What's its pressure? And so its pressure is 18. So there is 18 millimeters of mercury pressure inside that capsular space. And so if this were an ordinary blood vessel, and it were 10 millimeters of mercury pressure here, and I had 18 millimeters of mercury pressure on the outside, then it would be the opposite of a capillary. What would be occurring? Things would be going into the blood, if that were the case, right? Because this is a higher pressure than what would be inside. So I have to have a higher pressure here always as compared to my environmental pressure, the interstitial pressure that surrounds it. That's part of the why, that's not the whole story. Okay, questions before we start to move on? All right, let's sketch this out again real fast. All right, so far, we've said we have this 18 millimeters of mercury pressure on the outside, that's in the capsular space, but we have 60 millimeters of mercury inside the blood vessel, which seems like more than enough. So this, you can think of this as an inward pressure, and this as an outward pressure. But there are other issues that we have to contend with. We also have something called the colloid osmotic pressure. We have not talked about osmosis for quite some time. Osmosis, simple definition is water likes to go to wherever the higher solute concentration is, right? So this is my abbreviation for what osmosis is. It's water wanting to go wherever the higher solute concentration is. And what we have done by taking the water and some of the solutes out is we have really concentrated the proteins inside the blood. There's tons of proteins inside the bloodstream. And now there's lots of water outside the bloodstream. So water wants to go where those proteins are at, where the higher concentration of the proteins is at. And so water is actually now drawn back in to the blood vessel because of osmosis. It's attracted to the proteins. That is referred to as the colloid osmotic pressure. It's the attraction of H2O to the proteins that we have concentrated in the bloodstream. That pressure is 32, it's actually obviously quite high, 32 millimeters of mercury on average. So here's what we end up with. We end up with two pressures working against us that add up to 50, 18 and 32. Right? We end up with two pressures that are working against us that add up to 50 millimeters of mercury. Now remember what a normal capillary was, 10. So the reason I have to maintain 60 in here is because the difference between those two gets me to normal capillary pressure. So to sum up, the why are we maintaining such a high capillary pressure in this particular capillary? 10 is normal, 60 is really high. The reason that we are maintaining a high capillary pressure of 60 is because we have two other pressures that are working against us that want to drive fluids back into the blood vessel. 32 from that osmotic pressure and 18 from simply the capillary pressure that's out here. Those add up to 50, so I have to have at least 60 to get the job done of continuing to push things in that direction. We call that remainder the 10. We call that remainder the 10. We call that the net filtration pressure. So when I subtract the two other pressures, I'm left with 10. And so that's my net filtration pressure, which is now back on par with the kinds of pressures that we see elsewhere in the body. the very bottom, it basically, in a matter of words, tells us there is a risk now associated with kind of doing business this way. The 60s, based on the way the kidney operates, we have to maintain that high capillary pressure of 60. It's just the way that our kidney is built. But with that comes a risk. That's a very high capillary pressure. And so if one has high blood pressure, these blood vessels are kind of already running at their max. 60 is pretty high. So if we have high blood pressure, chronic high blood pressure, hypertension, that increases that 60 beyond norm, that blood vessel can rupture very easily. So even though hypertension is seen with the cardiovascular system, carries a potential risk associated with cardiovascular disease, dysfunction of the kidney urinary system is also a potential risk of having too high a blood pressure for too long, because those capillary blood vessels they're already maintaining a very high blood pressure. Okay, question on anything that we've covered. And just to summarize, we've talked about what this thing is made out of, the membrane, and then we talked about the two pressures working against each other, and the result of which is a net filtration pressure of 10 millimeters mercury, pushing things downstream. Questions? All right, simplistic drawing of what we've been discussing. We'll jump past that. Okay, some looks horrible. It's not as bad as it looks, but some simple calculations that can be produced once we have a few values that we can consider. Now we have at least one of those values, the net filtration pressure. So one of the things that we want to know with respect to good kidney health and function is what is the glomerular filtration rate, which is kind of like assessing the perfusion for the circulatory system, how much blood is flowing to a particular organ. We might ask how much fluid is being produced through this tube in a particular amount of time. So the glomerular filtration rate is exactly that. How much fluid is coming out of this tube? Now keep in mind, there's not just one of these tubes, there's millions of them, right? This is just one nephron, but in your kidney you have many. So of course it's all added up together, but we want to know how much fluid collectively is going into the proximal convoluted tubule. How much kidney filtration fluid we're producing gives me an indication of kidney health. So how do we calculate that? So the abbreviation is GFR, the glomerular filtration rate. And so the amount of time is kind of arbitrary, but we typically calculate it in a minute. So how much fluid is going into the proximal convoluted tubule, not of one, but of course of all of them, right? How much fluid is going into all of your proximal convoluted tubule in a minute? So we just need to know a couple of things. Net filtration pressure, which we have, times K of F. K of F is your filtration membrane space. So if you think about it, how much fluid you put into your proximal convoluted tubules will be dependent upon how much total blood vessel wall you have to work with. Let me give you an example. Do some erasing here. This one will work. Let's say we could if we can understand what happens in one of these, we just have to remember that it's happening in millions, but really nothing else changes. So let's pretend that a kidney just had one of those, that the entire kidney just was this structure. In reality, the entire kidney is basically just one of these structures, just happening on a micro scale billions of times, right? But let's compare two of these to define the K of F. All right, so here's another one. And here's the blood vessel going in, and here's the blood vessel going out. And so let's say one of them had that, and this one has this going on. Is the blood in here for a longer period of time? You betcha. So it is subjected to these filtration mechanisms for a much longer period of time, which means there's many more opportunities for things to escape the bloodstream than over here, right? There's very few opportunities for things to escape the bloodstream. So if we were comparing K of F, we would say this one over here has a high K of F, and this one over here has a low K of F. So K of F is basically a measurement of how much filtration membrane space is your blood exposed to. And so this one has a very long membrane filtration space that the blood is exposed to. So if I want to know how much of anything passes through a filter, like there's probably a filter in that thing right above my head, right? Like an air filter. Well, there's really just two things I need to know. How big is that filter, and how much force is behind it? And then I'll know how much air is going to make its way through, right? If the entire filter is this big, that little grate is, I don't know, 2 feet by 2 feet almost, but imagine instead it was that big. Not very much air is going to come through that, right? So the size of the filter will tell me how much fluid will pass through. That's one variable, K of F. And then the other variable, how much pressure is in this tube? How much force is behind, pushing? That's the other variable. So if I want to know how much fluid in total the kidney is going to filter, I need to know those two things. How much pressure there is pushing, and how big is the filtration membrane. So we're not going to actually make the calculation, as you can see here, right? No numbers are attributed to those. We just need to know what the two variables are, right? We just need to understand that there are two variables when it comes to determining that, that amount of fluid. So again, what's the pressure, what's the force pushing, and what is the filtration membrane space? So the 125 and 105 is as if we had those values and we've calculated it, and what we're looking at here is simply an average, right? To actually know the values, the NFP and the KFF, we have to investigate a person. So on average, here's how much fluid is passing into the proximal convoluted tubule, all of them, in a minute time. So for your average male, 125 milliliters per minute. For your average female, 105 milliliters per minute. If you extrapolate that, that means 180 liters, right? And a liter is a little bit bigger than that. So 100 of those for a male per day, and 150 of those for a female per day is how much is escaping the bloodstream. Why is it likely higher for a male on average? Do you think their NFP changes significantly? It does not. It's their KFF. That's changing. Why? Because men are bigger on average, so which means their kidneys are a little bit bigger than females on average. So their filtration membrane is bigger on average. So the NFP stays pretty much constant between males and females, but the KFF, which is just how big something is a little bit bigger in males, so therefore, on average, they filter a little bit more fluid. Okay, lastly, on this slide, as you can see, you're filtering out, let's just average it, let's just say 150, males, females combined, right? 150 liters per day. I don't know when the last time you really kept track of how much you urinate. It was probably and hopefully just a smidge under 150 liters, right? Which tells us that most of what gets filtered out goes eventually back into the bloodstream. Because if it stayed in here, if it really truly did stay in this tube, well then you would be urinating out 150 liters per day, which would kill you. And that's not happening, so that means that most of it gets put back. How much of it? 99%. So 99% of what we filter out actually gets put right back in. So we are incredibly over-filtering our blood, depending on your perspective. So we filter out 150 liters, maybe on average between males and females, and we end up actually putting back in all but 1 or 2 of those liters. So now let's play around with this for just a little bit. What would happen, and your options are simply up, down, or let's say no change, these are your options. What would happen to your GFR if you had a genetic disease that made your endothelium, your fenestrated endothelium, more permeable than it ordinarily is? It's more permeable. Right. What would happen to your glomerular filtration rate, the amount of fluid that ends up in this tube, if your fenestrated endothelium didn't change anything else, but now that's more permeable? Up. Because more fluid than ordinary, more solutes than ordinary are going to be coming out. So that goes up. And what did we change? We didn't change the pressure. We changed something about that filter, the KFF. We made it more permeable. What would happen to your GFR if, because of hypertension, we just lost, this whole thing ruptured, it burst because of high blood pressure? What would happen to your GFR? It would go down, because now your KFF is decreased. I just lost some of my filtration membrane space, so now I'm not producing any fluid in that tube anymore because my filter ruptured in that tube. So when the number of nephrons, which is what KFF is a measure of, when the number of those goes down, then our GFR must go down. Now what if, I'll give you another example, what if we lost some nephrons, but as a consequence, the pressure in other nephrons goes up? We might get to the point where for some time, it's like a wash, right? That I lost filtration membrane here, but that caused the pressure in other ones to go up. So in other words, KFF went down, but maybe NFP went up, and so now the two canceled each other out. So this is kind of a quick introduction, but we're gonna be discussing later kidney issues that affect GFR, and kind of making sound predictions on what would happen to GFR based on some changing variables. Questions so far? Yes?
So, of the 99% that gets recycled, is that where most of the water is pulled out, or is that later?
Most of the water is pulled out in the proximal convoluted tubule, and then still adjusting it further on down the line all the way to the collecting duct, but most of it is pulled back almost immediately from the proximal convoluted tube. Yes?
How does the body know what to take out? I don't know if we'll talk about that. Or
Yep, we will. No, it's a great question. Calcium, since it's right there. So you have chemoreceptors throughout the body that are constantly monitoring the levels of any particular thing. And so later on, if we lost some calcium, and we right now are, let's say, hypocalcemic, which means having lower than normal calcium levels, there are cells that line the proximal convoluted tubule that we can send hormones to, like parathyroid hormone and calcitriol, that will tell these cells, hey, we know that ordinarily you let calcium go by, but put a calcium pump on the surface of your cell and suck that calcium back out and send it to the bloodstream. So we're monitoring the levels in various locations in the body, and then communicating with these cells that are kind of watching this stuff flow by, and then we can tell them directly, hey, either capture it or don't capture it. Or capture more, capture less.
And this is a pretty fast process that happens. You said the hormones. That
You're right,
takes a long time.
exactly. So compared to the nervous system, well, we do have, there's limited, but there's a little bit of nervous system innervation. But yeah, most of it's through the endocrine system and hormones. We're talking about hours rather than, hey, we're gonna get the job done. Other questions? All right, so we've looked at how to calculate the GFR. We're just touching on so far like why it'll go up and why it might go down. But generically, we can say, hey, what are the consequences if it gets too high? What are the consequences if it gets too low? So if you have a glomerular filtration rate that is too high, again, that means that too much fluid is passing through and into the proximal convoluted tubule. It means that it might be moving so quickly that we lose the opportunity to recapture some of those important solutes. Like somebody flowing downstream in a rapid, well, that water speed is going to influence our ability to get them out of there, right? So if we have a GFR that's moving too quickly, now we lose opportunities to reclaim some of those solutes. So the net effect is high urine output. So instead of the 1 to 2, maybe 3 to 4 liters per day, which obviously is going to make us incredibly dehydrated. And because we're losing the ability to recapture some of those solutes, then we're also going to be low on electrolytes. Those would be like the immediate effects. Not listed would be like far more risky effects in significantly reducing blood pressure and having immediate cardiovascular failure. Right? So in other words, it can get that high where we have too little plasma in our blood to maintain good blood pressure. GFR too low, well, remember the primary thing that we're doing with all of this, which we've kind of not discussed in a while, is we're removing waste. Right? The whole point of this is to get things out of the blood that we don't want in the blood. So if our GFR is too low, that means nitrogenous and metabolic waste might begin to accumulate inside the bloodstream, which can cause problems. And generically, that's azotemia, when we're not efficiently getting rid of nitrogenous waste through the kidney, and that has its set of problems as well. So that's why it will be important to both understand what GFR is and how the body manipulates it, so that at any point in time, we have the right GFR, the right glomerular filtration rate. So more will be said about GFR, the manipulation of it. Okay, speaking of which, sorry, I thought I had this after the next section. We're just gonna go ahead and jump right into it. So it looks like, actually, today will be all glomerular filtration rate. So we've actually just, Joshua asked the question, and this alluded to the next topic. How and when do we tell the kidney to affect its own GFR? Increase it, decrease it, change something about what's happening with respect to pressure. We'll look at a few different examples. But there are three basic mechanisms by which we control the GFR. And obviously they're listed here. The first one, renal autoregulation. Renal autoregulation is basically the kidney self-assessing. So renal autoregulation is where the kidney, so this is one kidney, outflow, inflow, and then we have there. So even though this is for an entire kidney, you can see that really a kidney is basically just a big one of those, right? Inflow of blood, outflow of blood, a tube taking the waste, right? So the kidney is constantly monitoring its total GFR, how much fluid output it has. It has a default amount that it's looking for. And so if it's below or above, there are some adjustments that will be made. We'll talk about what those are. So that's all we mean by renal autoregulation. The kidney self-assessing, knowing that it has some, benchmark to hit. That this is the amount of fluid I want to produce. Let's just say it's 2 liters, right? That's where I want to be every day, and I'm not there. Well, I need to do something. So renal autoregulation, the kidney self-regulating its own filtration rate. Sympathetic control. Sympathetic control is the nervous system communicating to the kidney to change its GFR. So there's limited nervous system innervation here, but there is some. So sympathetic control would be where the nervous system plays a role. And the last one is hormonal control, kind of what we were just talking about, where we can, through the endocrine system, secrete certain specific hormones that will have an effect on our glomerular filtration rate. So we have 2 outward sources, and then we have renal autoregulation. It's kind of like the heart. The heart has its own intrinsic rhythm that the brain can tell it to speed up or slow down. The kidney has its own built-in filtration rate, and then the brain and the hormones, the endocrine system, both of those can modify the filtration rate. So that's kind of the generic introduction. We're going to take these one at a time. And with renal autoregulation, you'll see there's 2 subtypes. There's 2 different versions of renal autoregulation. So I don't think that top bullet says anything that I didn't just mention, but again, renal autoregulation is just the ability of the kidney to self-regulate, to auto-regulate its own glomerular filtration rate. So again, maintain stability. This bottom line here on the second bullet tells us kind of the most likely reason for the kidney to affect its own glomerular filtration rate. So if your systemic blood pressure goes up in your body, right, if the systemic blood pressure goes up in your body and we don't do anything, then glomerular filtration rate will go up. There's just no way around it, that if your total blood pressure goes up, then your glomerular filtration rate will go up. But if we want that to remain constant, with a changing blood pressure, so your blood pressure is going up, but I want that to be constant, well then something will have to be done. And then on the opposite is true as well. If your blood pressure is dropping, but for whatever reason I want to maintain a constant GFR, then something will have to be done. So without these mechanisms, your glomerular filtration rate would just follow whatever your blood pressure does. If your blood pressure goes up, your GFR goes up. If your GFR, if your blood pressure goes down, your GFR goes down. So if we didn't have these mechanisms, those two would just be correlated to each other. It's literally cause and effect, actually. So that's the primary reason. Are there other reasons why we might affect GFR? There are, but that would be the major factor that influences when and why the kidney will change its own GFR. Get rid of this absolute chicken scratch over here. And then, like I said, for renal autoregulation, there are actually two different ways that we can go about it. The first one's real simple, the second one's less simple, but there are two ways. So the two ways are down here. There's what we call the myogenic mechanism, and then there is the tubuloglomerular feedback system. Myo, what do you think that's in reference to? Myo. Muscle. Good. Myo is in reference to muscle. Tubulo, that's in reference to the tubes, the PCT, the DCT, the tubes of the nephron. So one is in reference to muscle, and we'll talk about who's muscle. One's in reference to muscle, and one's in reference to the tubes of the nephron. So we're going to take the myogenic mechanism first. A lot on this slide, but the concept is pretty straightforward. When I drew this the other day, I said you guys are really tired of me drawing this thing. All right, so again, we've already said it, the afferent has to be of a larger diameter than the efferent so that we maintain that high pressure here. If we have high systemic blood pressure, so our blood pressure is high, it could be because we are worked up about something. It could be because we're going for a jog, or it could be just because we have hypertension. But for whatever reason, our atrial blood pressure is higher than it ought to be, so we have high blood pressure. If we didn't do anything, like we already said straightforward, if we didn't do anything, if we have high blood pressure in our body, it's going to increase that value. We said that the pressure there is 60 millimeters of mercury, but if my blood pressure increases out here, invariably that will increase the pressure there, and that will then increase the GFR, because remember, the GFR is the net filtration pressure times K of F. So if I increase this, I'm going to increase the net filtration pressure, which will then increase the glomerular filtration rate. So I don't want that to occur. I don't want my external systemic body blood pressure to affect the pressure in my kidney. So how do I stave off an increasing pressure here from having a pressure there? It's pretty simple. All I do is squeeze a little bit on this blood vessel. Think about the garden hose, right? I talked about reaching your hands around it earlier, but imagine, you realize the end of the garden hose is on and you turn it on and it's spraying. You just kink the water hose, right? You just pinch it, and now there is reduced blood pressure this direction, and there's higher blood pressure back that direction. So if we have systemic high blood pressure, what the smooth muscle in the afferent arteriole is going to do, it's just going to contract a little bit. It's just going to squeeze a little bit. And that keeps my high blood pressure back there in my body. And it reduces the pressure in here, in the capsules, because blood is flowing in that direction. So if you momentarily have high blood pressure, that's going to squeeze. Going up a flight of stairs, temporarily, your blood pressure is probably going to go up a little bit. Eventually that blood pressure might begin to return to normal, and if it does, we're just going to start to relax. that blood vessel. So pretty simply, the only thing, well, not the only thing, but one of the things that I have to do to maintain that 60 is monitor what's going on out there. And when it goes up, I begin to squeeze. And when it begins to go down, I relax. And we just keep that on an endless loop. And that's the myogenic mechanism in a nutshell. Squeezing and relaxing that afferent arteriole. If somebody has really low blood pressure, again, just the opposite's gonna happen. We're gonna dilate this thing as big as we can get it to get more blood in there and maintain that blood pressure. Questions on the myogenic mechanism? Okay, the next one is the more complicated out of the two. Tubulo-glomerular feedback mechanism. What has not been articulated yet, because we didn't necessarily need to talk about it yet, is the fact that this tube, the proximal convoluted tubule, which we now know goes into the loop of Henle, and then we said that it becomes the distal convoluted tubule. But I'm not a model maker, but for whatever reason, they chose not to represent this in the models. But the DCT, when the DCT comes back up, it actually, oh, this is a horrible drawing. The DCT flows back by the entry into the capsule. So let's just go back to at least one picture that I think does a pretty good job of this, that we jump past this one. So here's the proximal convoluted tubule. There's the loop of Henle. Now notice that distal convoluted tubule goes right back by the entry. It almost makes it look like it goes back in. It doesn't. It just turns back by. This one does as well, right? So even though it has a short loop of Henle, the distal convoluted tubule goes right back by the entry point. So proximal convoluted tubule, twisting and turning, loop of Henle, the distal convoluted tubule goes back by our blood vessels. So understanding that anatomy is important to understanding this process. There are, I can't remember, okay, probably have to I'm going to say a few more things, but I'm going to provide the details later. So the generic of this is that you have a group of cells that are surrounding the distal convoluted tubule right outside the capsule. And they're basically, this is cells looking, these little eyeballs, okay? They're watching, I don't know, that one's out of it. Anyway, they're watching fluid go through the distal convoluted tubule. They're watching the fluid. And they're basically like measuring how much fluid is passing through that tube. And so in essence, they are measuring the glomerular filtration rate. They're just watching the fluid pass by. And they can determine if there is too much or too little. And then they will send commands to the blood vessels to either constrict or dilate, which is going to change my GFR. Just as an example, if they detect a lower than normal flow rate, what will they tell the afferent arteriole to do? Relax or contract? Relax. Good. Excellent. Right? They're going to tell that blood vessel to relax. Let more fluid in. That way more fluid will make it to where they're at. Okay? We're going to expand on that just a little bit. Next week we're going to run out of time here and there's more details that I can't fit into our last 3 minutes. But, well, I guess actually we'll just stop. Okay? probably start that over from scratch, since it'll be quite some time since we will have discussed it. So on Monday, when we get back from Turkey Day, we'll come back and describe these mechanisms of theft via